Bible has a lot to say about the natural world and God's relation to the natural world. I think there's probably more in the Hebrew Bible about God's relationship to the natural world than there is in the New Testament, which mainly focuses on the doings and sayings of Jesus and of the relationships of the members of the early church. But the Hebrew Bible, the Old Testament as we call it, has a lot of statements like these that you see on this slide. In the beginning, God created the heavens and the earth. And God said, let the water under the sky be gathered to one place and let dry ground appear. In the Psalms we read, the heavens declare the glory of God, the skies proclaim the works of his hands. Psalm 104, how many are your works, Lord? In wisdom you made them all. The earth is full of your creatures. There is the sea, vast and spacious, teeming with creatures beyond number, living things both large and small. By wisdom the Lord laid the earth's foundations. Here's an interesting statement from Jeremiah. This is what the Lord says. If I have not made my covenant with day and night and established the laws of heaven and earth, then I will reject the descendants of Jacob and David, which is a rhetorical way of saying, yes, I did establish my covenant. Yes, I did establish the laws of heaven and earth, and so I will never reject the descendants of Jacob and David. So we see these references to the natural world and to God's laws. Do you know the laws of heaven? We read in Job. He also made the stars, and God saw that it was good. In Genesis, God saw all that he had made, and it was very good. So there are many statements like this in the Old Testament. And so if we look at all of these truth claims, these are assertions about the physical world and God's relationship to it, we can ask, what is it we learn about God? What is it we learn about his relationship to the world? Well, the physical world was made by God, so says the Bible. God made it in wisdom, by understanding, by his knowledge. The world obeys laws established by God, and the world tells us something about God. The heavens declare, the skies proclaim. The physical world is good. God saw that it was good. Whatever that means. Does that mean nothing bad's going to happen? What does that mean? We're going to look at what that might mean. We don't read that the world is perfect. God did not see that all that he made was perfect, but it was good. And that it had a beginning. So statements like these make the case that the universe is displaying evidence of God's wisdom and his understanding and his knowledge. And by the way, wisdom, what does that mean? Well, it implies that creation is not accidental or haphazard or whimsical. It has a purpose. There's a reason God did it, and God thought hard about it, presumably. Creation required planning and skill. And also, it's possible that humans may not be able to grasp all of it or understand all of it, although, since we are made in God's image, perhaps we can understand a good deal of it. So these are some of the claims I want to look a little more closely at tonight, especially in light of modern science and what we now understand about the universe. But here's something we need to keep in mind. Biblical writers assumed a Mesopotamian cosmology. There is stuff in the Old Testament that just does not agree with what we understand today about the way the physical world works, the way the earth looks. Now, in this Mesopotamian cosmology, and you see a diagram of it here on the left-hand side of the figure, there is an ocean that surrounds the dome or the firmament of the stars and planets. If you're like me, you went most of your life without knowing what the word firmament actually meant, but it's a dome. In this cosmology, the earth is flat. It's encompassed by an ocean around and beneath the earth. And there are many biblical passages that refer to this picture. They sort of refer to this picture in passing rather than making a lot of assertions that this is really the way it is, and you better write this down because you're going to need this. It's not like that. It's just that this is assumed in Job. Who shakes the earth out of its place and its pillars tremble? Here are the pillars of the earth holding the earth up in the middle of this primeval ocean. The earth trembled and quaked. The foundations of the heavens shook. What are the foundations of the heavens? Well, they are mountains on the horizon, which are presumably holding up the firmament of stars. He stretches out the heavens like a tent and lays the beams of his upper chambers on the waters. So you see, there is this upper ocean up above the firmament of stars that contains water. And then this passage from Psalms implies God constructs the heavens then on top of that ocean. Now, there are similar views about the world that you can find in many ancient traditions, from all the way from Celtic to Hindu. This was a fairly widespread cosmology. Now, if you look at this, this is not an arbitrary model. It's a model. We would say it's not a very useful model in modern terms, but there's a reason this model looks the way it does.
Stand back from the back.
Just, okay. Sorry. Look at what this model explains. Well, for one thing, we know that water rains down from the sky. What's that mean? There has to be water up there somehow. So the ancients conceived of an ocean up there above us. The sky is blue. Well, the sea is blue, and so again, maybe that's water up there. We know there's water up there. So they conceived of an ocean of water. We know today, of course, we do live at the bottom of an ocean, but it's an ocean of air, not an ocean of water. We know that water rises up to the surface of the earth from below, so there must be water down there under the earth, so maybe there's water all around the earth. We also know that water recirculates from the earth to the sky, so maybe there's a connection out here between the primeval ocean around the earth and the ocean of heaven up above the earth. So you see, this model is not arbitrary. It's intended to explain various observed facts, but it's just not a model that we would find useful today. And it's nevertheless assumed by the writers of the Bible. So there's more in this Mesopotamian view of looking at the world. There's a whole creation myth about how it all came to be. There are documents like the Atrahasis and the Enuma Elish and the Epic of Gilgamesh. You may have heard of these stories that bear some similarity to Genesis, but I want to show you some of the details here of the Enuma Elish in particular, which is the Babylonian epic story of how the universe came to be. And it is the story of a battle. The Enuma Elish is this long sort of novel about conflict among the gods and a rebellion by some gods against Marduk, the main god, who is the good guy in this story. And it culminates in a battle between Marduk and Tiamat. And so here's a drawing taken from an inscription in a Babylonian ruin in Mesopotamia, in present-day Iraq. And the Enuma Elish says, then Marduk returned to Tiamat. Marduk's the good guy, Tiamat's the monster, whom he had subdued. The Lord trod upon the hinder part of Tiamat, and with his unsparing club, he split her skull. He cut the arteries of her blood and caused the north wind to carry it to out-of-the-way places. He split her open like a muscle into two parts. Half of her he set in place and formed the sky therewith as a roof. So that's what the sky is. We're looking at half of the body of Tiamat, and then we look up at the stars. Marduk creates mankind from the blood of a vanquished enemy, Kingu, who is the husband of Tiamat. So elsewhere in the Enuma Elish, we read that as Marduk hears the words of the gods, his heart prompts him to create ingenious things, and so he thinks about what he's going to do. He says, blood will I form and cause bone to be, and we will create man. And so Kingu it was who created the strife. It was Kingu, the husband of Tiamat, who duped her into rebelling. Do you see any kind of a parallel maybe with Genesis chapter 2, you know, a couple who went wrong? So anyway, it was basically Kingu's fault. So they bound Kingu and held him. Punishment they inflicted upon him by cutting the arteries of his blood. With this blood, they created mankind. Marduk imposed the services of the gods upon mankind and set the gods free. So that's why humans were created, to do the work of the gods. Isn't this a convenient epic if you're the ruling class of Babylon and you have to explain to your slaves why they better get back to work? You know, this is a very practical religion here for such a hierarchical society. Well, when you read the Enuma Elish, and it goes on like this for pages and pages, it's fun reading, you know, but it's kind of a novel of strife among the gods. And you compare this to Genesis. In the Genesis account, God does not struggle with an enemy. He does not make things out of pre-existing bodies. He does not create humans to do the God's work. Now, I'll have to say that compared to the Enuma Elish, Genesis seems to be just the facts. You know, whereas I'm sorry to say the Enuma Elish seems kind of like a made-up story, and I'm sorry if the Enuma Elish is your foundational scripture, but I just have to say that. I mean, I imagine an early Mesopotamian reading the Enuma Elish and thinking, man, this is total BS. You know, this cannot be what happened. You know, I doubt there's a Tiamat or a Marduk. So who was that? Was that Abraham, possibly, or somebody whose name we've lost? Well, we don't know, but I see a huge contrast between Genesis chapter 1 and Enuma Elish. Now, there are some parallels. I pointed out this notion of a couple, a husband and a wife going bad. You know, okay, that's perhaps reminiscent of Adam and Eve. There are also references to Marduk resting, perhaps like God rests on the seventh day of creation, but Marduk rests when he sits and contemplates the dead body of Tiamat and, you know, what to do. So it's a different kind of resting. Here is a passage that refers to the Enuma Elish and how Marduk creates the stars of the zodiac and creates stations for the stars. And that's sort of reminiscent of Genesis chapter 1, where God creates the lights in heaven that give us light during the day and night, and the stars. But the overwhelming impression, I have to say, and this is probably a personal thing, I encourage you to take a look at the English, you'll enjoy it, is that Genesis is very different from the English. But now I want to look at this claim that the universe had a beginning, as we read in Genesis chapter 1. In the beginning, God created the heavens and the earth. Now, is that just one of these details that could have been wrong, like God creating laying the beams of heaven on the ocean above the stars, which is just a wrong view of the universe? What should we say about the claim that the universe had a beginning? Was that just a lucky guess, maybe, by these Mesopotamian writers? Or could that be part of this, I would say, more likely divine inspiration, or perhaps the work of a religious genius in the terminology of William James, whoever discovered monotheism or invented it, or it was revealed to? Well, if it was divine inspiration, why didn't God inspire the writer of Genesis to tell us about quantum mechanics or relativity or galaxies or orbital motion or the water cycle or dinosaurs? Why were all those details left out? Well, when you ask questions like that, it's wise to keep in mind, first of all, that ancient desert nomads didn't really need to know modern science, so you would have been wasting a lot of cuneiform tablets and writing that stuff down. But furthermore, it is best to approach the Bible as a poetic work concerned with ethics and religious behavior, our relationship to God and his relationship to us. It does not yield to close scientific correlations. And so various writers here, this is the New Bible Dictionary, here's J.J. Davis saying that the Bible is primarily concerned with the meaning and purpose of God's work and leaves out many, many details, as you know. But I want to say that the notion of a beginning is not just one of these details that might have been wrong, detail of Mesopotamian cosmology. I want to say that's a fundamental aspect of the universe that we read about in the Bible. But it's a controversial notion because, well, many ancient thinkers debated whether the universe actually is eternal or not. And how could we ever know? Aristotle and Epicurus both taught that the universe is infinitely old and has always existed. That's an intellectually appealing idea, actually. It means there's a whole lot you perhaps don't need to explain. But this presented a big problem for Christianity in the 12th century when universities were springing up all over Europe and new good translations of the Greek thinkers like Aristotle were being introduced, translated from Arabic sources who had preserved and written about the Greek thinkers. Averroes and Avicenna were very important Muslim commentators on the Greek philosophers. Aristotle was very influential in Europe, but much of Aristotle directly contradicts biblical teaching. Thomas Aquinas and his teacher, Albertus Magnus, Albert the Great, knew Aristotle was very important, and they somehow had to reconcile Aristotle with Christianity. And Aquinas argued that even if the universe was eternal and infinitely old, God could have created it anyway. That is, God is outside that thing. We now understand the universe to be a four-dimensional object. And God could perhaps be outside of it. This is what Aquinas said. Of course, 800 years ago, he did not speak in relativistic terms of 4D space-time, but I think it was a remarkable insight on his part. God could have created the world without preceding it in time, because there was no time axis at that point. In fact, so by the 19th century, most scientists agreed that the universe is infinitely old. As I said, this is an intellectually appealing, simple idea. Why not? Isaac Newton concluded the universe had to be infinitely large because he had invented the inverse square law of gravity. He realized, you know, you're going to just have all the stars collapsing on themselves if you have a finite assembly of mass. It's just going to all get sucked up into a big, he wouldn't have said black hole, but it would all fall together. So he reasoned that the universe had to be infinite. There had to be an infinite distribution of mass so that the potential would be constant and the gradient of the potential would vanish inside that distribution and you would not collapse. So good thinking on Newton's part. Immanuel Kant, a little later than Newton, reasoned that the universe has to be infinitely old because Kant believed that an infinite being, his notion of God, could not be restricted with dealing with just a finite universe. And if it's infinitely large, maybe it's also infinitely old. Albert Einstein, you know, had to add a term to his gravitational field equations, the cosmological constant, to explain why the universe is static. Because without that cosmological constant, again, Einstein faces this problem that Newton faced, that you would get a gravitational collapse. So Einstein needed to put that lambda term in there to hold everything up. Einstein, of course, lived long enough to see lots of data showing that the universe is not static, but we'll get to that in a minute. Now, this idea of an eternal, infinite universe poses various problems and paradoxes. And if you're as old as I am, you remember a time when there were lots of people still clinging to the idea that the universe is static and eternal. And you may remember these paradoxes. Olbers Paradox. If the universe is infinite, why is the sky dark at night? In every direction you look, you should see a star. It should be, you know, the sky should be solidly bright as the surface of the sun all the time, everywhere. That's Olbers Paradox. The Kelvin Paradox, which came up during the development of thermodynamics during the 19th century, asks, if the universe is infinitely old, why isn't the entropy of the universe infinite? Because entropy increases monotonically with time. The universe should be in a completely equilibrium state. And it's, in fact, we observe it's very, very far from equilibrium. And then I sort of invented this, I'm kind of proud of this, the Fermi-Olbers Paradox. You've heard of Fermi Paradox. Where is everybody? If there are all these other civilizations out there in space, where is everybody? You know, why haven't we been visited? And so I combined it with Olbers Paradox and said, if the universe is infinitely old, why haven't we been visited an infinite number of times by an infinite number of advanced civilizations arriving from an infinite number of places? Anyway, so you see these problems posed by an infinite universe. Well, but then things began to change. And in the 20th century, then evidence emerged that the universe is not static, that it's expanding. And so Slipher discovered in 1912 that many galaxies are moving away from us. They're receding from us. Henrietta Leavitt had discovered over the period 1908 to 1912 a method of measuring distance to a certain kind of star called a Cepheid. And if you can find a Cepheid in the galaxy, you can measure that'll tell you how far away that galaxy is. So then Hubble, over the period 1924 to 1929, used these discoveries by Slipher and Leavitt to show that the more distant a galaxy is from us, the faster it is moving away from us. And if you think about that, what that means is that the universe is expanding, and it's expanding uniformly, and it would look the same way from any place in the universe. It's not that we are in a special place and everything's moving away from us. No, it would look that way no matter what galaxy you were in. So if everything is getting farther and farther from everything else, what does that mean? think backwards in time, what it means is that in the past, everything was a lot closer together. And in fact, if you think far enough backwards in time, everything had to be all at the same place at some point in the past. Well, it's from reasoning like that then that the idea of the Big Bang originated. And we now believe that in fact, 13.7 billion years ago, yes, indeed, all matter and energy in the universe, and in fact, all space and time, was concentrated in a very, very tiny volume, maybe a point. We just really don't know because we don't have a theory of quantum gravity to tell us really what happens at that point. But there was some kind of event 13.7 billion years ago that we refer to as the Big Bang. In fact, the development and expansion away from that point, we call that the Big Bang. And so now the Big Bang is a very securely established model for the universe's history. It explains many observed facts about the universe. And here is a diagram, a nice diagram. You know, it's a two-dimensional picture of the expansion of a sort of a two-dimensional surface along a third time axis. So it can't really show us what a four-dimensional object would look like, but the Big Bang would be here on the left-hand side, and then 13.7 billion years later, here we are at the present time, and various events along the way are pointed out here. This model explains the expansion of the universe, the cosmic microwave background. It gives an account of where the deuterium and helium came from, the areas of decoupling, and I'm sorry I won't have time to say much about this tonight, and the formation of galaxies and galaxy clusters. So I will say a little bit more about this, but the point is many lines of evidence show us that the universe did have a beginning, and it is not infinitely old. There's a very good book by Martin Rees called Just Six Numbers, The Deep Forces That Shape the Universe. And he says in this book that the Big Bang Theory has lived dangerously for more than 30 years. He published the book in 1999. So I changed 30 to 50 because 20 years later, there is no reason to change any of his conclusions. There are many ways you could have proved the Big Bang Theory is wrong, okay? You could have found that, you might have found an astronomical object with zero helium, okay? Or with much less than 23%, or with helium that's much less than 23% of the hydrogen abundance. But no such object has been formed. That's a good thing because the Big Bang explains exactly why there is 23% as much helium as hydrogen. You can have discovered that the cosmic microwave background radiation did not have a thermal blackbody spectrum, but it does have a blackbody spectrum to an extremely high degree of accuracy. You could have discovered that neutrinos have a higher mass than they apparently do, and that would have scotched the idea of cosmic expansion. You could have found out that deuterium didn't have the right abundance to match theory, and so forth. You could have found that the fluctuations in the cosmic microwave background were inconsistent with the present-day large-scale structure of the universe, and so forth, and many other tests. So the Big Bang Theory has survived all these tests. It's a very satisfactory theory. Now, I want to get to the idea of why the universe might be considered good. And what was God getting at when he talked about, when he saw that the universe was good? Let's talk about the cosmological principle, and we'll get to the anthropic principle. The cosmological principle follows from the work of Copernicus, who of course showed that the Earth is not at the center of the universe, or not even at the center of the solar system. It's not at the center of very much at all. So the cosmological principle is a generalization of that idea. It says that viewed on sufficiently large distance scales, there are no preferred directions or preferred places in the universe, least of all the Earth. All places look pretty much the same. That's the cosmological principle. This is clearly not true on short distance scales. Clearly, the Earth does not look a lot like any other planet in the solar system. But so this is a statement that averaged over large enough scales, everywhere in the universe looks pretty much the same. But the anthropic principle now was enunciated in the late 1900s, and it was propounded to stand in contrast to the cosmological principle. The anthropic principle says, well, at least we are here. And what does that mean? It states that the universe appears surprisingly hospitable to the emergence of life, even complex multicellular life, in at least one particular place and time, namely the Earth. So here we are. We look around and we don't see many other folks like us in the solar system or indeed in the galaxy so far. Now that could change. We may find advanced life on other planets any day now. Many reasons not to think that that's very likely, which I won't go into in much depth, but anyway, the anthropic principle is attributed to Brandon Carter, a cosmologist, who said that although our situation is not necessarily central, it is inevitably privileged to some extent. You know, a lot of things have to have gone right for us to be here where we are today. Alfred Russel Wallace, as long ago as 1903, said it may be that this vast and complex universe is absolutely required in order for us to be here where we are today. That is, complex life to be here today. So this is the anthropic principle. And when I think about what God might have meant when he saw that his creation was good, I'm thinking perhaps it has to do with this idea that the universe is precisely tailored to do something. For one thing, to allow complex physics, biology, and conscious minds like our own. Martin Rees's book, Just Six Numbers, points out that there are at least 6 numbers that I will go through here whose values are crucial for life to exist in the universe. These are the ratio, and these, by the way, are dimensionless numbers. So for those of you who are physicists or scientifically trained, you're familiar with the idea of a dimensionless ratio, which is important because it means that it doesn't matter what system of measurement you use, whether you measure quantities in terms of feet or miles or seconds or fortnights. A dimensionless number doesn't depend on what units you use to create that number. So the ratio of forces, for example, is dimensionless. So there's this first number is the ratio of the force of gravity to the force of electromagnetism. There's a ratio of the nuclear force, the strength of the nuclear force to the strength of electromagnetism. There's the density of the universe, expressed in appropriately non-dimensional units. Cosmological constant, which basically is the expansion rate of the universe, the texture of the universe I'll talk about, and then the number of space dimensions, which is 3. And I'll just point out that in 2 dimensions, orbits would not be stable. In 3 dimensions, you can have orbits that are stable. Good thing for us. Let's look at some of these numbers in just a little bit of detail. The strength of the nuclear force compared to the strength of the electromagnetic force. This affects nuclear fusion. So a little bit of detail about nuclear fusion. If you take a pound of hydrogen and fuse the nuclei together, all of them, to make helium, you'll discover that the mass of the helium weighs only 99.7% as much as the mass of the hydrogen you had to fuse. What happened? What did I say? 99.3% as much as the mass of the hydrogen. What happened to that other 0.7% of the mass? Well, it was converted to energy. And that's why fusion produces energy. This delta M is called the mass defect of fusion, and it is a measure of the strength of the nuclear force that holds the fusing particles together. So let's call that strength 0.7%. What if the nuclear force were weaker, say, so that delta M was only 0.6%? Well, in that case, a proton couldn't bind to a neutron. You could not make deuterium. You could not make a stable deuterium nucleus. Deuterium is called heavy hydrogen. It's a nucleus where a proton and a neutron are bound. This means you can't produce helium in the Big Bang because deuterium is a stepping stone on the way to the production of helium. If you can't make helium, then you can't make any elements more massive than helium in stars, which is where heavier elements are produced. So you have a periodic table with only one element in it, hydrogen. You have a universe that's very, very boring. You don't get any physics except the physics of hydrogen nuclei moving around. On the other hand, what if the nuclear force were stronger so that delta M was 0.8%? Well, now protons can bind to other protons. You could create a stable nucleus with just two protons bound together, which, by the way, is impossible in our universe. This means that all the hydrogen would have fused with other hydrogen during the Big Bang. So there would not be any hydrogen remaining. This would be a really bizarre universe, but one thing it would mean is that there could be no water, which depends, of course, on hydrogen. H2O is the formula for water. So no water, no biology, no biochemistry, no life. Once again, a very boring universe. So our good universe has delta M right where it needs to be, 0.7. There are other processes. The creation of carbon actually requires delta M to be tuned a good deal more closely than just 0.6 to 0.8. That, by the way, is about a 15% variation from 0.7 to 0.8, let's say. So the production of carbon requires delta M to be tuned to just a few percent. Let's talk about this idea of the texture of the universe. This is this other number Q. By the texture, we are referring to the lumpiness of mass in the universe right after the Big Bang. If the Big Bang had been extremely smooth, let's say the density had been extremely uniform in that very first few picoseconds of the Big Bang, well, you would not have formed galaxy clusters. Gas would never have condensed into gravitationally bound structures at all, given the current expansion rate, or the expansion rate of the universe at that point. And once again, you get a very boring universe, just full of gas, no stars, no galaxies, no black holes, no life. If, on the other hand, the universe had been much lumpier, so this number, this texture number, had been smaller than the observed value, then the universe would have been an extremely violent place. It would have been filled with vast black holes, sort of nothing but black holes. Again, no stars, galaxies, planets, no stable planetary systems. Once again, you might say that's a more interesting universe, but in fact, it's probably pretty boring because the black holes in general do not interact very much. Here, by the way, is the diagram of the microwave sky as determined by the WMAP satellite, showing fluctuations in this 3-degree Kelvin black body radiation, multiplied by a factor of 10 to the 5th, so we can see these fluctuations. In fact, you know, the microwave background is extremely smooth, and you could say the universe is pretty smooth, except it's just right. It's good, okay? The texture is just right so that we do have galactic structures and so forth. Here, this lower diagram is a map of the density of galaxies today. And these two very different kinds of observations, microwaves versus galaxies, they are very closely consistent with each other. In other words, you can show that the current galactic structure was produced by an early Big Bang that had just this degree of roughness in the radiation emitted in the early epochs of the Big Bang. So the bottom line is the universe is very boring unless its properties are carefully set. So I'm speculating here that what the biblical writers were getting at, although they could not have known, most likely, when they wrote that God saw that what he had made and called it good, was that the universe is very well tailored to do what God needed it to do. When God said the universe is good, or saw that it was good, I don't think he was thinking, that means nothing bad will ever happen. We'll never have any evil things going on. I think it may mean that, like any artisan, God was satisfied with what he made. He looked at what he had made and said, yeah, that's right. It conformed to what he wanted. It conformed to his will. And this was his will, that the universe have these properties. Now, there are many other properties besides these that are important for life. For example, the initial entropy of the universe and the strength of the weak force, which is a force that's important in radioactive decay. There are many other properties that ought to go on this list of properly tailored attributes of the universe. Now, I haven't even mentioned the properties of the Earth, of our planet Earth, that are unusually tailored so that life can exist. There's a very good book by Ward and Brownlee called Rare Earth, Why Complex Life is Uncommon in the Universe, which outlines the arguments here very, very well. So the rare earth idea just compounds the notion that our existence required very, very precise control of the universe and the earth and the way things are today. Now, what if you're an atheist? What if you're a non-theist and you look at all this? How do you account for this fine-tuning? So it's as if all these numbers have been very carefully set. Well, here's where we encounter the idea of the multiverse. Maybe there are many, many other universes, something like ours, but with different values of those fundamental constants. In fact, with random values. Maybe there is a sort of a universe producing phenomenon out there beyond our universe. I think of a waterfall or a bonfire producing, ever fluctuating streams and eddies and vortices and little structures, flames or whirlpools, depending on your model. And maybe there's something that produces universes the same way. And all those universes have different properties, randomly chosen. And there are many, 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 many of these. And so, sure, one of them just happened for no reason to have the properties we need so that we can be here today. And of course, that's the one we're in. We couldn't be in any of those other universes. So no big deal. It's like you check into a hotel and your room number is your birthday. You check into room 626 and your birthday is June 26th. And you say, oh, it's incredible. God knew I was coming and here's my room. Well, no, it's just that, like there are a whole lot of room numbers in the hotel and you just randomly happen to get one that's your birthday. Or let's say you buy clothes that fit. You go into a department store and you find clothes that they fit you exactly right. Incredible, what a coincidence. No, it's just that there are all kinds of clothes with all kinds of sizes and you pick up the ones that fit. So this is the multiverse idea, that there's no big deal about our universe. Well, okay, we'll pursue that a little bit, but on the other hand, you could say, isn't it more like you have been walking along and you find a guy flipping a coin? He's flipping a coin, and you notice it always comes up heads. He flips and flips and flips, and he flips 100 heads in a row. What do you say? You say, oh, there must be about 10 to the 30th other coin flippers out there somewhere, and I just happened to run into the guy who flipped 100 in a row because, you know, the odds of flipping 100 in a row are like 1 in 10 to the 30th. Is that what you do? No. You look at the coin, don't you? Or you look at the guy and say, how are you doing that? So I think as we think about the multiverse, you want to apply Occam's razor, I think, and let's keep things simple. Okay, what data demand that there be a multiverse? I think what we find is that cosmology puts atheists in a tight spot. Lawrence Krauss, writing in Nature in 2003, says, most physicists have hoped that an ultimate physical explanation of reality would explain why the universe must look precisely the way it does, rather than why it more often than not would not. I think this is not the easiest sentence in the world to parse, but what he's saying is that science is telling us the universe ought to look anything other than like what it looks like. So cosmology is telling us that the universe ought not to be the way it is. Maybe this is the definition of a miracle, but anyway. So if you're an atheist, you're kind of backed into a corner here. You have to say there's a multiverse. It's the effect of some universe producing random cause. Quantum fluctuations, we know that there are quantum fluctuations, that is, particles pop into and out of existence, especially in the presence of strong fields, strong electromagnetic fields, for example, produce pairs, electron and positron pairs, and it's possible that universes are huge quantum fluctuations, and they're therefore very improbable, but perhaps that's where the multiverse comes from. But you have to believe that the multiverse cannot contain a cause of which our particular universe is the necessary effect. That would be way too theistic, wouldn't it? Someone made the argument that our universe is, yeah, there's a multiverse out there, but we're here because something special went on in another multiverse, and it made us. I think that's a very short step away from saying, well, yeah, that's God. So I think atheists don't want to go there. And so if you believe in the multiverse, you cannot seek an explanation for why our particular universe is the way it is. That part of science is over for you. And this sounds to me like the multiverse of the gaps, as a termination of science, at least that small part of science that seeks to explain why our universe is the way it is. Religious believers are sometimes criticized on the basis of invoking a God of the gaps. Like if there's a gap in our understanding, well, that must be God. God helps us bridge that gap. Well, here I think we see atheists doing basically the same thing, saying, we can't understand why the universe is the way it is. Got to be a multiverse. You got to believe. You just got to believe. Okay. There's no data, there's no evidence, but you got to believe. So I think this is kind of an intellectually problematic, philosophically problematic place you get to because of the discovery that our universe has a beginning in time and that its properties are very, very carefully tailored to allow us to be here. Now, there's plenty of science to do, even if you're an atheist. One is that we need to understand more about the Big Bang, but to do that, we're going to need a theory of quantum gravity. We're going to need to understand how gravity works when all of the gravitating mass is combined in an extremely small space on the order of the wavelength of the particles at play. There are contenders. There's a very good article in a recent issue, the February issue of Scientific American this year, that discusses string theory and loop quantum gravity, which are contenders, and I won't take time to go through these diagrams. So that, just to say, there has been progress in this very interesting aspect of physics that will, we hope, explain more about the Big Bang and what goes on in black holes, for that matter. Now, there's lots more. And so I think we can agree with Pierre Teilhard de Chardin that creation is not finished. And here I am grateful to Professor Marty Hewlett for this slide. He was our first speaker this summer, and this slide, I think, bears strongly on this idea of why God saw the universe as good, why it satisfied his will, what God has in mind for the universe. Because Teilhard listed these properties, these phenomena of the universe. If you view the universe as a drama, as John Haught does, the theologian who visited us a few years ago, then the drama is occurring in several acts, let's see. There's cosmogenesis, the evolution of the physical universe, which I've been talking about tonight. There is biogenesis, the appearance of life in the universe. There is psychogenesis in these stages outlined by Teilhard, the evolution of consciousness. And by consciousness, then we can consider a range of animals who are no doubt conscious, but are not human animals. You know your dog is conscious, of course. Probably lizards are conscious. And so we see conscious minds appearing. Teilhard refers to noogenesis, which is the evolution of mind, and here I think we do refer to human minds, reflective thought. In Teilhard's conjecture, the universe is moving towards the omega point, union with God. Hard to know exactly what this all would mean, but the idea here, of course, is that the universe is doing something. The universe is here for a reason, and it satisfies God's will. In many respects, it's not perfect, but it is good. So that brings me to the conclusion of the talk. I appreciate your attention. There are some questions on the table that I hope we can use for further discussion, but thank you very much.
Too close to.
Sure. So when we thank you. So when you talk about the multiverse, isn't it that it's not that it's just random traces of numbers, right? It's usually an infinite multiverse, meaning that there's infinite number of them, and so right, it is not that you're just randomly flipping and you just randomly choose numbers. It is an infinite multiverse that has infinite right variations of it, and so there's every single possible variation with every single possible combination of the 6 constants, right? And you have we are just sort of in just a particular one, right? So that was the thing that what I heard usually before is the idea of a multiverse. Not you don't have just number of multiverses and there's just particular random numbers, right? It's an infinite multiverse. There's infinite number of them. So that's one thing. And the other thing, right, to my best knowledge, right, living theory sort of we go back to a singular point, but we never cannot go beyond that, right? And so it still doesn't sort of rule out the idea of a previously collapsing universe, right? So you had we are in a state of expansion, right? But there is not necessarily none of what you said sort of refutes this idea that there previously was a contraction, right? So do you have comments on that?
Yeah, thank you, Michael. On the multiverse, there are sort of three chief models for what the multiverse is, in my limited reading about the multiverse. I think what you're referring to is the quantum many worlds multiverse, which is the idea that quantum mechanics, one interpretation of quantum mechanics would invoke this quantum many worlds multiverse, so that at any event, in any event where quantum mechanics predicts a probability of several outcomes to the event, quantum mechanics being a probabilistic formulation of mechanics, that new universes are spinning off that follow the various possible outcomes of that event. And since there are, well, infinitely many events, presumably any particle collision counts as an event, then our universe is spawning off universes all the time. There are infinitely many. But in that viewpoint, all those universes need to have the fundamental properties that our universe has. Right now, I mean, if this, let's say this many worlds process is going on during the Big Bang, then yes, perhaps that would be a mechanism for generating an infinite number of universes that could have had different properties. So that's the quantum many worlds idea of the multiverse. But another idea of the multiverse is that our universe, this universe, has many regions that we cannot contact. We know there's sort of a horizon to our universe beyond which we can't see. And so maybe at the time of the Big Bang, our universe kind of spawned off other little, I think of them as protrusions, you know, like an amoeba will extrude little sections of itself. So I imagine our universe doing something like that. And those other little sections of our universe might have had different properties. And maybe there were many, many of them, and we just happened to be in the one that had the right properties for us to be here. But there would not be an infinite number in that case. Then the third idea is that, no, there really are a very large number of disconnected universes. So this is like a slight variation of that second idea where those parts of the universe that perhaps got spawned off, they actually got disconnected and they're floating around out there somehow in another dimension, not our four familiar dimensions of space and time. And again, there are not an infinite number. I've heard 10 to the 500th power as a plausible number based on some formulations of string theory. Okay, and perhaps 10 to the 500th is enough that you would expect one like ours to come along every now and then. So three ideas for the multiverse. Your second question had to do with what? Remind me.
I was talking about, the idea of Big Bang doesn't necessarily involve the idea of previous contraction, right? So,
oh yeah, could not our universe have followed the contraction of a prior universe? So in other words, the singularity at the beginning, 13.7 billion years ago, was that just the bounce from an earlier universe that had contracted down to that point? And perhaps this cycle has been going on eternally. An expanding and collapsing universe. This idea is similar to a concept of Stephen Hawking's, which he describes in his book, A Brief History of Time. And I read that book again in preparing for this talk, and it was very interesting to read it after a lapse of 20 or 30 years probably. What he says in that book is that he was pretty excited by this idea because he had the idea that although entropy increases with time in our expanding universe, perhaps entropy would decrease with time in a contracting universe, and that could explain why the Big Bang singularity had the low entropy that it apparently did, since we observe the universe, at least parts of the universe, to have pretty low entropy today. But several of his co-workers prove to him later on, and Hawking describes this in his book, prove to him that actually entropy would increase even in a contracting universe with time. And then, once again, what this gets you into is the Kelvin paradox. That if the universe can go through cycles of contraction and expansion, we must be in the first one because of the low entropy of the universe. And certainly if this cycling had been going on infinitely long, well, then our universe would have infinite entropy right now. We would be one of, just a big mist of gas in equilibrium and nothing else. So could there have been maybe a couple of cycles of contraction and expansion? I don't know, but it seems unlikely because, again, based on this entropy argument. So Hawking describes this, very straightforwardly. He says, yeah, I thought it was a good idea, but, they convinced me it wouldn't work.
We'll do one from the Zoom audience and then one from.
You want to stand over?
Yes, thank you. Here's the question. Sorry, a question from Joyce Guzik. This delta M argument depends on the mass of the proton. What would happen if the proton mass were greater or smaller? Would all of the arguments hold just at a larger or smaller scale?
Yep. Thank you, Joyce. I don't know a lot about, quantum chromodynamics, the strong force, but just as a detail, I'm not sure. It depends on the mass of the proton or neutron. I think it depends on the color charge of the quarks that make up the proton and the neutron. That's a detail. I think your question basically means, couldn't we rearrange the properties of those nucleons and the quarks to sort of compensate for a change in the
So, for example,
mass defect? I suppose there's a degree of that kind of retuning that could go on.
I didn't know where wanted, and I was.
If the nuclear force were stronger, couldn't we compensate for that by making the electromagnetic force a little stronger, so that
Sorry, are you?
protons still couldn't fuse? Okay, right? It's the fact that the nuclear force overcomes the electromagnetic repulsion of the protons. Let's see, in our universe, the nuclear force does not overcome the repulsion of the protons, fortunately, and so hydrogen can't fuse. So if we were in danger of being in a universe where the protons could fuse, and just boosting the strength of electric repulsion ought to compensate for that, right? Okay, so I think that's your question, Joyce. And yeah, I suppose there's some amount of that can be done. But if you're going to change electromagnetism, then maybe you got to change gravity too, because
I'm trying to explain the scientific position
and you better change biology too, because biology depends on the electrical interaction of particles during chemistry. So if you're going to change one thing, you're going to have to change a lot of other things that go along with it. And probably that's an interesting direction for future research, but to me, the answer is not simple. I think you've got to make a lot of compensating changes, and whether that works or not, I just don't know.
I'm surprised that there's so many churches too, although I'd never had that shock feeling that you had. But the reason is, I would think that there'd be a lot more atheists.
If I understand your Chardin conclusion to get to the omega point, that there's three people who do that. Jack Hott does it, Marty Hewitt does it, and of course they're following Chardin. If you look at evolution, though, evolution is very slow.
It seems like
takes absolutely forever to get to consciousness. And then it took thousands, tens of thousands of years, probably hundreds of thousands of years to get to self-consciousness. And so getting to this omega point, if I just worry about how long it takes to move in these directions, do you expect that omega point, something might happen to make that omega point happen tomorrow rather than a million years from now?
Not necessarily.
Because if it's going to take that long, human beings aren't going to be around.
The Big Bang. I mean,
Well, as Teilhard might have said, au contraire. You know,
I
don't think it took a very long time at all for us to get here. You know, one of the early objections to the Big Bang notion came from Arthur Eddington, who basically said, no, there would not have been enough time for life to appear. All these folks who wanted the universe to be infinitely old realized, or in their way of thinking, you know, motivated by Darwin to a great extent, it's going to take a very, very long time
in physics
for life to appear and then for organisms of various types to develop. They were not happy with the notion of a universe that could perhaps be as young as 13.7 billion years. You know, life appeared on the Earth very shortly after the era of initial bombardment by meteorites in the solar system. Within a tenth of a billion years, there was life on Earth. No, it's very short. Yeah. Okay, so this is a matter of taste. I mean, compared to infinity, 13.7 billion years is.
I'm not glad to do the mushrooms. I think I can wait till the morning. I don't know. They're probably better off.
I mean, what looks long to you looks short to somebody else, and it's just relative to what?
Well, I think he's open enough. You know, I think it's a good faith effort to, you know, I don't think he's.
So I too have two questions. The first one is, I don't know that much about multiverses, but it sounds like all of the ones you had talked about so far involve sort of a single set of axioms or constants across them. Is it possible that there are there formulations of multiverses that are just completely different, that fundamental forces don't exist or are different or lacking, or these ratios, or, you know, is there a universe where physicists don't care about a 137?
Well, that's a good question, Daniel. Yeah, I don't know enough about, let's say, string theory, I guess, to know what is possible. But you have to believe that a universe would be possible where there's basically nothing, you know, no mass, no energy, maybe some space, maybe some time, but otherwise, you know, empty. I guess that's a possibility. And then why not versions of that extremely simple and boring universe that have just a little bit more complexity and so forth, all the way up a ladder of complexity. But who knows? I'm just speculating.
My second question is about your statement of the anthropic principle. I had always understood the anthropic principle to be like, suppose that only 1 in every 10 to the 30th universes supports life and consciousness. But for all those other universes, that there wouldn't be any conscious beings there to appreciate this low probability event, whereas in the ones that are, that's where they would be. So it seems like you might be able to reframe that and look at it as not all that remarkable relative to the probabilities.
Yeah, I said the initial formulation of the anthropic principle was to make it stand in contrast to the cosmological principle. And now people have had a lot of fun elaborating the anthropic principle, so that you hear about the weak anthropic principle and the strong anthropic principle. And some people will cast it in the terms you just did, which is that no matter where we find ourselves, it won't be that big a deal because it has to be that way for us to be there. And that you could imagine Brandon Carter was saying that, but in fact, he was trying to say something that contrasts with the cosmological principle.
We're going to take one more question from our Zoom audience.
Thank you. This is from Steve Sizz or CZ. He says, if other intelligent life is found, does it impact anthropomorphic universe?
Since our universe seems to be custom tailored to permit life, it seems like a real shame if there were not lots and lots of other planets where life exists. So I think we should be optimistic that we will find life elsewhere in the universe. But and in fact, that book, Rare Earth, I referred to by Ward and Brownlee, they say it seems likely that we will find microbial life on other planets elsewhere in the galaxy, in fact. They argue, however, that complex life, let's say multicellular life, is very unlikely, but they hold out hope for microbial life. And I think, let's hope we find something because it will be very interesting, whatever we find, wherever we find it. If we don't, then I think you encounter a really sobering notion of how improbable our existence is, but which leads to interesting conclusions of its own, I guess. But I think let's keep looking for life elsewhere. I think that will just help make the point that our universe is indeed a very special place. It allows life.
Should be more blessed to have such a fantastic speaker for our last speaker of the summer session. And I know we just clapped for him, but can we clap for him again and say thank you very much? Good job. Good job. So at the tables, there are questions, and pick the ones that you find most entertaining. And Nels will wander around to as many tables as he can and join you in conversation. And we'll try to get Nels to address our Zoom audience as well. Again, thank you very much for joining us this season, and we will be back. Thank you.
Do I disconnect?
How are you all doing tonight?